Hi, this is Dr. David Branham. Today we're going to be covering Chapter 8 of your assigned reading. That's quantitative analysis and descriptive statistics. This is a video that's meant to be a supplement for your reading, but as I've said before, I try to be pretty comprehensive in these videos, so it should help you a lot with your tests. So I'm going to start by sharing the screen and getting PowerPoint up. So this is quantitative analysis, descriptive statistics, as I said. When it comes to descriptive statistics, that previous chapter, chapter 7, covered the experimental design. And experimental design is inferential analysis that statistically tests a hypothesis. It's theory testing. That was in the previous chapter. But this is on descriptive analysis. So it refers to statistically describing and aggregating and presenting these constructs of interest or associations between constructs. So a lot of times we use the terminology of variables and constructs intertwined. But what we do is we take, we see a variable that's interesting to us, and we want to describe it sometimes with a single number. Sometimes we describe it in comparison to others. So in this chapter, we're going to examine the statistical techniques used for descriptive analysis. And these are actually quite simple in comparison to the exploratory science techniques that we used previously. In data preparation, so what we do is when we get data is we have to prepare it. And there are several different ways that we can collect data. We can collect mail-in surveys, interviews, pre-test and post-test experimental data, observational data. We have all kinds of data that we collect in science. And so there's a lot of different ways to do it. So after we collect this data, we need to prepare it. And this data has to be converted into a machine-readable numeric format, like a spreadsheet, so that they can be analyzed by computer programs like PSPP or SPSS or R or Stata. Those statistical programs are usually where we put our data in. And from there, we are able to convert it into both descriptive data, or if we want to, we can do those exploratory analyses like t-tests and so forth for our experimental designs or our regression equations. Data preparation usually follows the following steps. First, you have data coding, then you enter your data entry, then you have to deal with your missing values, and then you do data transformation. And we'll go over these for this chapter. First, data coding. Coding is the process of converting data into numerical format. In most cases, we use a code book for this, and code books are very important, especially if you have a large data set. Even if you don't have a code book, the person who is doing the data coding has a code book in his or her head, even if it's a small data set, because they have to organize the data. So a code book can be created to guide the coding process. A code book is a comprehensive document containing detailed description of each variable in a research study. So when you get data, sometimes you receive it. If you receive data from the outside, sometimes you'll receive it in a spreadsheet, and sometimes it's, for instance, an SPSS statistical package or Stata, but it usually comes with a code book. Some statistical packages like Stata allows you to actually put the code book into the package, and that's very convenient. So coding is very important because without it, you'll lose track of your variables and a lot of mistakes will be made. So what is a code book? A code book describes the contents, structure, and layout of a data collection. A well-documented code book contains information intended to be complete and self-explanatory for each variable in the data file. The main body of the code book contains unambiguous variable level details. And these include things that are shown from the National Longitudinal Survey of Youth in 1979. You can see the entry for the codes. It says the survey year up there is, and now they say it was a youth survey for 1979. Here, the survey code book shows that the survey year was 2002. So in general, it says first it has the codes, and then It's got SF12, which is the assessment of ours general health. So they're assessing the respondent's general health with a series of questions. And this question is, in general, would you say your health is? And so from there, it gives you 5 possible responses: excellent, very good, good, fair, or poor. So you can see that it has them coded: 1 for excellent, 2 for very good, 3 for good, 4 for fair, 5 for poor. So this makes for easy coding of the variables into these categories. And then on the left of that, you see the number of people who describe their health as that. For instance, 1 excellent, 1,232 people described their health as excellent. 2,111 described it as very good. 1,531 said good. 563 said fair, and only 145 said poor, which is nice. That, you know, it was about 2% who said they were poor. So you had a total of 5,582 people answer the question. 6 people refused to answer the question. You can see that. That's going to be coded -1. So the others have 1, 2, 3, 4, and 5. Refusal will be -1. People who said they don't know will be coded as -2. In this particular question, nobody said they didn't know. 6 people said they refused, but no one said they didn't know. So that had 0 respondents. So a total of number of people asked was 5,588. So this is basically the code, what you put in the code book. So if you get a data set, you can read that question. You can come through and read that question and look at this. I have a very good idea of what's going on in that data set from that question. And I know the next question will probably be another assessment of the respondent's general health. And they'll have because that's the category. So variable information in a code book. These are typical. Some code books vary from this a little bit, but this is typically what they'll do. They'll put the variable name, the name or number assigned to each variable in a data collection. Some researchers prefer mnemonic abbreviations like employee 1. So they ask, where are you employed? And they'll put employee 1 as the name. Most of these names need to be eight digits or less. So a lot of researchers like to use numbers. For instance, you see on the next one, variable 001, which is VAR 001. It's nice code where you can put the variables in 6. Now, if you get all the way up to 999 variables, you're still at 8 or less. So this started back when SPSS first came out. Your variable name had to be 8 or less. So everybody had a system of coding the variable name where they had eight or less digits or numbers in that code. So for survey data, try to name the variables after question numbers. For instance, like Q1, Q2, so forth. That helps. And a lot of times what the researcher will do later is he'll take out the variables that he or she doesn't want. They'll put in new names for those variables so they'll be easier to see what they are. In a lot of cases, you know, what they'll have is Q1, and then when you push your cursor on Q1, then the variable label will come up. Now, the variable label is a brief description to identify the variable for the user. It should be short, but it doesn't have to be short. Where possible, you would use the exact question wording. So if you're doing a survey on the variable label, you just put the exact question. In general, your health is. That would be the question, and that would be the variable label. So the question text, where applicable, the exact wording of the survey questions would be what you want in the code book, because that tells the person reading the code book exactly what was said, and it helps them understand exactly what that variable is doing. Values, the actual coded values in the data are for this variable. So remember, we have 1, 2, 3, 4, 5. We had -1, -2, -2 for don't know, -1 for refuse to answer, and then you have 1, 2, 3, 4, 5, starting at excellent down to 5. That just tells the number that you put in for those. Now, if you're a researcher, you probably want to recode that, because when you do your analysis, for instance, when you do a regression analysis, you want to recode into a line that's consistent with the data that you need to do. So you may not want excellent to be 1. You may want it to be 5. You want, personally, I would want to reverse this, where excellent was the highest level of health that you thought you would be in. And so that would be 5, and 1 would be poor, which means that's the lowest level. So a lot of variables will be recoded. If you do categorical variables in 1 and 2, which almost everyone does, 1 yes, 2 no, you want to convert those no's to 0. And that way you can do probant logit analysis. So later on down the line, researchers will recode all those variables. But it's important just to know what they are right away. So you put these in, and if the researcher concede, oh, they coded this one yes, and they put no as 2, I know how to recode that, and that's not an issue. Now, summary statistics, where appropriate and depending on the variable type, you provide an unweighted summary statistic for quick reference. For categorical variables, for instance, frequency counts showing the number of times a value occurs and the percentage of cases that value represents for the variable appropriate. For continuous variables, you want to put the minimum and maximum and the median values, which are relevant. So you want some descriptive statistics there for your continuous variables. So as I say, if you're doing a categorical variable or a dummy variable, which is basically a yes or no, you want to say what percentage said yes, what percentage said no, what number said yes, what number said no. For instance, if you had 200 people in your survey, 120 said yes, 80 said no, you put in 120 yes, 80 no, 60% said yes, 40% said no. That's what you're going to want for your summary statistics. Now, if you have continuous variables, you want description. What is the average? What is the median? What is the minimum? And so forth. You want that description in your code book. Missing data, where applicable, the values and labels of missing data should be, you should have that valued and labeled. Now, what you want to do with missing data depends on the researcher. I personally think listwise deletion is the way to go on missing data. I don't like imputation. I've tried imputation. I think it biases your results in a lot of cases, or it waters down your results. So it reduces your validity by biasing it, reduces your reliability by watering down your variables. For instance, if you put an average in there, you're just making your variance smaller, and that doesn't help your statistical analysis. So I'm one who likes listwise deletion. If you're going to use a variable that someone didn't respond to it, you throw out the whole responded. That's the way to go usually. And now you lose a lot of data when you do that, but you don't have problems with bias, validity, and reliability issues as much if you just use listwise deletion. That's my opinion. But missing data, you just put in there what is missing. For instance, refusal, -1. You coded it -1. So if you want to find out who's missing, go to all the -1s. If you want to, you might want to actually code somebody who says they don't know on a question. Not knowing something may not be something you want to throw out. So you may want to code that. So the researcher should put a code in that for that data. Universe skip patterns, where applicable, information about the population to which the variable refers, as well as preceding variables and so forth. So, these are little things that you like to put in to help. Also, additional notes or remarks or comments that help you contextualize the information conveyed in the variable or relay specific instructions. For measures or questions from copyrighted instruments, the notes field is the appropriate location to cite the source. So that's important, because if they cite that source and it's copyrighted, you should also cite that in your paper. It's important that you make that note. When a code book is important, coding and a well-organized code book are especially important for large, complex studies involving many variables and measurement items, where the coding process is conducted by different people to help the coding team code the data in a consistent manner. Make sure everybody knows, they're getting together. If it's missing, it's -1. Don't leave it blank. Put in -1. Make sure everybody has a full understanding of how the data should be coding if you have multiple people doing it. A lot of times you'll get a teaching assistant or an intern to do your data coding. Sometimes it's just a student in your class. Although if you're getting several people, you need to make sure they're all on the same page. Otherwise, you'll have a mess and your data will be destroyed. Coding can destroy your data. If you have a large data set, you have to have a code book. If you have a smaller data set, sometimes you can put it into your SPSS or Stata. Sometimes you can just do it on an Excel sheet. But you got to have some notes to tell you what these variables are. And so it's very important. If you have a large data set, please do a very good code book, because otherwise you will ruin your data. Data entry. Coded data can be entered to a spreadsheet, database, text file, or directly into a statistical program like SPSS, PSPP, or Stata. I've gotten data from all of these sources. I can convert all of these sources to the package I need. If I have it in a text file, I can get it in a text file and convert it to SPSS or Stata. That's not an issue for me. So if you run into this later on down the line and you have problems, give me a call. I'm happy to help you as long as I can help you. If you have a text file, how do you convert your text file? I'm happy to do that. Sometimes some of you already know how to do that because you've done it for other things besides data. But converting this data can be done, and it's not that difficult once you learn how to do it. If you sit down and give it some time, you can do it. Smaller data sets with less than 65,000 observations and 256 items, you can store that on Microsoft Excel. I like to store a lot of stuff on Microsoft Excel because it's really easy to convert Microsoft Excel into SPSS or Stata, which Stata is my favorite statistical program because I can do so many things in it that I can't do in others. So, but converting an Excel file to Stata, it's not an issue. It's easy to do. So here I put in an SPSS spreadsheet just so you can see what one looks like. If you have PSPP, which is free, and I will, you can always get PSPP. Don't put it on your Mac, but you can, if you don't have a Mac, you can get PSPP for free. Yeah, you can also get SPSS for a pretty cheap price sometimes, especially if you get the smaller packages. Each observation can be entered as one row in a spreadsheet, and each measurement item can be represented as one column. So let's say you have a variable gender. So where would you put gender? Gender is a variable. You would put that as a column. So the very first variable you may name it what you want. For instance, I would name it gender, and you could have it, for instance, coded 1 is male, 0 is female. So you can code it, or vice versa, whichever one you pick. But you make sure that you code it and that you put the note down in the code. This is what they're coded as, so that people won't get mixed up. So obviously, if you're looking at gender, then your unit of analysis is a person. So each number on the side will be a person. So you code 1, the person's person 1, put their gender down as 1 or 0 in the first variable. On down, all the way down to say you have 500 people, you can get number 500. You're going to put gender in for each one of them, coded. And so that's what you do for the first variable. Then the second variable you put in where the var is. It's another column all completely, and you put in the data for each person on that. So that's how you do the SPSS spreadsheet or an Excel spreadsheet. If you do an Excel spreadsheet, you have 1 to infinity. Across are the variables, down are the units of analysis. In most cases, a unit of analysis in survey research is the person, but you can have unit analysis as the school. So you put, 1 through 50 would be the schools. Your first variable may be school name. And so you can put that down as a string variable so you can easily read the school name. And then you'll have other variables for the school, for instance, enrollment, test scores, and so forth. Those are all be variables. Variables always go down in columns. unit of analysis across in the numbers. So missing values, we talked a little bit about missing values, but missing data is an inevitable part of any empirical research set or data set. Respondents may not answer certain questions if they are ambiguously worded or too sensitive. So one, during data entry, some statistical programs automatically treat blank entries as missing values. That's fine, you can do that. If you do an SPSS, all it has is a little period. Most of the time in SPSS, people code missing data as 9. Especially if you're having these code variables like gender and so forth, where there's a limited number of observations. That's what usually they do. I don't like 9. I like for missing to be a blank box personally, because it automatically does list-wise deletion for you in SPSS if you do that. So I like blank, but you just need to decide beforehand and put in what you want to do. Some statistical programs automatically treat blank entries as missing values. So if that's the case, don't leave it blank if it's not missing. Okay. During data analysis, the default mode of handling missing values in most software programs is simply to drop the observation containing even a single missing value in a technique called list-wise deletion. That's what I was talking about earlier. I personally like this list-wise deletion. So, sometimes if you put in, usually the most sensitive question is, what is your income? Now you get more sensitive questions like that, but it's rare that those questions get put in to data. But in almost every case, income is a sensitive question. If you have income as a variable, in most cases, the best thing to do is put your most sensitive questions last. And if you're a good survey reader, they'll basically read it like any other question, and you'll get a better chance of getting a response. But the most sensitive questions could be last, because sensitive questions can end your survey. Now, if you end it on income, the most sensitive question, and it's the last question, then you still have the data on the rest. So if you want to throw out income, you still have that person's data. But if you want to do list-wise deletion, the missing any variable in your analysis will take that person out. And so that can actually cause a bias, but it is the easiest way to avoid bias by trying to use imputation to fill in missing data, by trying to put in the person's income and making an average. Okay, let's just put in the average income of 150,000 or 50,000 or whatever it is. You don't want to do that, because it really makes your reliability a lot lower if you do that. Such deletion can significantly shrink the list-wise deletion can significantly shrink the sample size and make it extremely difficult to detect smaller effects. But it is better than what I'm presenting here, which I believe is problematic. Imputation. Some software programs allow the option of replacing missing values with an estimated value via a process called imputation. Typically, the imputed value is the average of the respondents' responses to the remaining items on that scale. You can see imputation may be biased if the missing values are systematic. So people may not be answering a question for a certain reason. For instance, have you ever been in jail? If you have been in jail, you're going to resist answering that question, or you're going to think twice about answering. Everybody else is going to say no. And so you have a bias there. You've biased this so you may impute, people may impute that those people haven't went to jail, when the reality is that probably most of the people have been to jail who are refusing to answer that question. So that is a problem with bias and imputation that I don't like. I think it's better just to leave it blank if people refuse to answer. And that's the type of question that you probably shouldn't be asking if you really want truthful answers in survey research. So while list-wise deletion causes a lot of observations and has its own biases, it's preferred over imputation. Data transformation, and I talked a little bit about this before too, but data transformation is going to be important. It's a big job. if you get a data, say you go to Pew Research and you get a data set in SPSS and you import it, the one thing you're going to have to do, because they're going to give you the code book, they're going to give you the data, they're going to tell you what the numbers all mean, but you are going to have to transform that for your analysis. So sometimes it's necessary to transform your values before they can be meaningfully interpreted. For instance, a variable coded 1 for yes and 2 for no needs to be recoded to 1 for yes and 0 for no. So you can do the proper analysis for these things like probe it and log it, if that's your dependent variable, or if you just want to make it an independent variable in regression, it's better to have that 1-0 coding for all categorical variables. And it doesn't matter which one is 1 and which one is 0. This isn't about the value that you're not putting a value on the respondent. What you're doing is you're putting a code on what the respondent is saying, so you can properly look and see what's going on with that variable. With practice, it's easy to do these transformations. You do them very quickly. When you do your transformations, it's going to be very important that you recode, that you have a place where you recode those variables. So be sure and do that. Univariate analysis, or an analysis of a single variable, refers to a set of statistical techniques that can describe the general properties of one variable. Univariate statistics include a frequency distribution, and you've seen that in the code book, right? Central tendency and dispersion. Frequency distribution. Let me scroll right back up to it. Right here, you had that frequency distribution on that variable. In general, would you say your health is? Excellent, 1232. Very good, 2111, and so forth. In a frequency distribution, it's usually a good idea. You could have it in this form right here, where you see excellent, very good, and so forth, and you have the number off to the side. A lot of people like to put these in bar charts. I like to see them in bar charts where you can get a quick look and you can see really quickly, without looking at numbers and trying to calculate numbers in your head, really what's the dynamics of this variable, where very good is going to be a lot higher bar and poor is going to be this little bar over here on the far right. So a lot of times these frequency distributions look really good in bar charts, but it depends on, if you have it coded into nice compartments. If you ask a question like, how many days did you go to work last year? And the people answer it, you're not going to be able to make a frequency distribution of that, because the variance in the answers is going to be so wide that you're not going to be able to make a bar chart that wide. And the bars are going to be small because, it's not going to be easy to tell, get a good sense of it. Now, one thing you could do is collapse it, like 180 to 190 days and then put a bar, 191 to 200 days and then put a bar. That can help you make a bar chart if you want to do it like that. But frequency distributions of variables like that, where you have such wide variation in the answers, are not good, and they either need to be collapsed or they need to be adjusted in a way to present the data correctly. So you could also do measures of central tendency, and those measures we'll talk about in a second. And then there's dispersion, measures of dispersion. These are very important. The measures of dispersion are much more important in statistics than people think about in everyday life. So I'll go over those as well. So look at these frequency distributions here, right? So this frequency distribution of variable is a summary of the frequency or percentages of the individual values or ranges of the values of that variable. And you can see on the left here, I have another example where the frequency never, once per year, several times a year, and so forth. That's the frequency, and you can present that table. That looks good, and then that percentage right next to it, that looks good. If you were to put that in a table in a paper, that would look fine. So you could have that. Here we have a measure of religiosity, where we have a construct measured by the categorical scale. How many days do you attend religious services? So the thought here is that the construct is well measured of religiosity, is well measured by how much you actually attend religious services. It's intellectually pleasing, right? It's a pretty good way to measure it. Now, it could be measured in other ways as well. You can ask other questions to measure it, but it's a good measure. So you have a category here that gives you several answers: never, once a year, several times per year, about once per month, several times per month, several times per week. Now I see how it is there, but these answers seem to have an overlap on them. Several times per week doesn't have an overlap. Several times per month and several times per year has an overlap. About once a month and several times per year may be the exact same thing. I don't know. So I have my problems with how they coded this, but you can see in the frequency distribution on the right where they put the bar charts in, they basically made the categories, and they made the categories in the order that they thought had the most value for religiosity. And so you can see never, there's 85 people said never. So 85 out of 284, or about 30%, never go to religious services at all. They would have a 0 on the religiosity scale. And then you'd have people who actually go several times a week. 21 people, several times a week. 7% of the people will have very high religiosity score because they go to the religious services several times a week. So you have that scale, and then at the end you have the did not answer. Notice that they didn't put that in the item values, the did not answer, because they wanted to make it where you can kind of see the scale on the variable, and they wanted to ignore the people who didn't want to answer the question. But you should put that in your frequency table on the left. That makes sense. Maybe not for the bar chart, but for the table on the left, it makes sense because people need to know what percentage of people just refuse to answer the question. The distribution can be depicted in a bar chart or in that panel on the left. It's fine. Either way is good. Now, you have these measures of central tendency that we talked about in 2 slides ago, where you can describe a set of data with a measure of central tendency. And central tendency is an estimate of the center of a distribution of values. So there are 3 major estimates of central tendency. There are the mean, the median, and the mode. And a lot of you already know about these, but the mean is just the arithmetic average. And it's highly valuable in describing. Like if you wanted to see a hitter in baseball, a lot of times you can look at a hitter over and over again. You can't tell who's the best hitter. It's hard to tell. But if someone were to ask, what's his batting average or her batting average? And you know that one's batting average is 350 and another is 250. You have a single statistic there that describes a whole distribution of at-bats, what this person did with the whole distribution of at-bats. And that single descriptive statistic of central tendency gives you a good idea of who the better hitter is. It may not be perfect, but you know from looking at it, 350 is just a lot better than 250. Somebody who gets a hit 35% of the time is better than a person who gets a hit 25% of the time. The median is a good example too of a measure of central tendency. It's especially valuable if your distributions aren't normal. For instance, income. Income is a non-normal distribution because on that left side of the income is pretty much 98% of the population. People making 50,000 are there in the bump and so forth. But then you get out to the right of the distribution. People like Rihanna, Oprah Winfrey, Tiger Woods, Bill Gates, all of these people making incredibly huge sums of money. Donald Trump, I'll put him in there. He's a billionaire. Those people are making a whole lot of money. So when you put them into the pile of a measure of central tendency like the mean, they really skew the mean, and they really don't tell people what's going on. With the mean in the income distribution, perhaps 75 to 80% of the people are actually below the mean because of the Donald Trumps and Bill Gates and Tiger Woods and Oprah Winfrey's of the world who have billions of dollars and are pulling that mean way over to the right. And so the mean isn't really a good doesn't really give people a good idea of income distribution. This is a case where the median may be good. where it shows you that the central point. The median is the middle of the distribution. And so the middle of the distribution is going to be a lot lower, and it's going to give you a good idea what normal people make as far as income goes. And then the last one is the mode, which is the observation that occurs most often. So we'll go over these. So the mean, the arithmetic mean, and it's often simply called the mean. And if you're asked to do anything to calculate a mean in this class, it'll be really simple. So, but it's important to understand how to do it. So the arithmetic mean is often simply called the mean, or is the simple average of all the values of a given distribution. And so my example is my last 8 golf scores. I did put my last golf score on here because I shot it yesterday and it's worse than all these, so I left it off. And I did the PowerPoint before that, but I put the values up there of the golf scores. So if you want to find out my mean golf score, it's, I have 8 golf scores there: 76, 80, 80, 75, 83, 74, 79, 81. To find the mean, you just add those golf scores up and divide it by the number of golf scores there. And if you do that, it's 78.5. So before yesterday, my mean golf score of my previous 8 scores was 78.5. So my average score in mean is 78.5, and on those distributions. So that's a simple way to calculate the arithmetic mean. The median is the second measure of central tendency that we covered, is the middle value within a range of values in a distribution. This is computed by sorting all the values in the distribution in increasing order, or from the lowest to the highest. And then you select the middle value. Now, if you have a huge data set, this is kind of hard to do, but it's not that hard if you can just scroll through your data, right? If you have 5,000 people that you surveyed, you can scroll down to 2,520. You can sort first by your variable, and then scroll down to 2,500 and 2,501. That's where your median is. So in the case when there's 2 middle values, for instance, with 8 golf scores, there's 2 middle values. There's the 4th best and the 5th best. So if you have 2 middle values, there's an even number. This happens when there's an even number in your distribution. The average of the 2 middle values is considered the mean. So in my golf score distribution, last 8 golf scores, my scores, if I sort them from lowest to highest, they're 74, 75, 76, 79, 80, 80, 81, 83. So I know the middle 2 observations are the 4th and 5th, 79 and 80. So the median is the center observation of the distribution. So since there are 2 center observations, which were 79 and 80, you go to the 2 center observations and you take the average of those 2, and that average is 79.5. That's usually easy to see just with your eyes, that it's 79.5. The actual calculation is 79 plus 80, which equals 159 divided by 2, which is 79.5. But you can usually see that right there. If your middle 2 values are 74 and 76, your median is 75. So that's the easy way to get the median. So in this case, my average golf score or mean golf score is 78.5, but my median is 79.5. And then there's the mode, which is the most frequently occurring value in the distribution. And my golf score distributions were 74, 75, 76, 79, 80, 80, 81, 83. Only twice did I shoot the same score, and that's 80. So my mode would be 80. In the distribution of golf scores, the most frequent was 80. It was twice. The 80, therefore, is the mode. So note that any value that is estimated from a sample, such as a mean, a median, or mode, or any of the later estimates like that, are called a statistic. So if you get a test question and say which one of these are a statistic, you see the mean, it is a statistic. You see the median, yes, it's a statistic. If you see a standard deviation, that is a statistic. So know that for your test. A statistic is any value that is estimated from a sample, such as a mean, a median, or mode, or any of the later estimates that we are collecting from sample. Okay, dispersion. Now, dispersion is the third thing we were talking about. First, we did frequency charts. Then we did measures of central tendency, which were mean, median, and mode. Now it's dispersion. The dispersion of your data is very important. And as I said in the previous chapter video, for instance, the t-test, important part of the t-test is how much variance you have in your sample. I used the example of the ages of people going to a movie. And if it was a child's movie, the variance is very small. Everybody's 3, 4, or 5 years old. If it's an adult movie, it may be from 8 to 80, and it's got a wide variance. That's called dispersion. Dispersion refers to the way values are spread around the central tendency. For example, how tightly or how widely are the values clustered around the mean? Two common measures of dispersion are the range and the standard deviation. The standard deviation, the second measure of dispersion, corrects for such outliers by using a formula that takes into account the how far each distribution is from the mean. But the range basically looks at the highest value and the lowest value and subtracts the lowest value from the highest value and gives you a number, which is the range. So in a distribution, let's go back to my golf statistic. In a distribution, excuse me, my golf distribution here, where I had 74, 75, 76, 79, 80, 81, 83, my range here would be 9. It would be my highest golf score, 83, minus my lowest golf score, which would be 74. So my range would be 9. And that would tell us how much dispersion there is in the data. The problem is it doesn't tell us anything about the 6 in the middle. It only tells us about the 2 on the outside, the 74 and the 83. If you count my score from yesterday in there, then all of a sudden the range gets a lot bigger because my score yesterday was a lot higher than 83. I'm going to keep it under wraps. But that is a flaw. That is the flaw in the range. It only looks at 2 values to try to calculate something for the entire data set. So the good thing about the standard deviation is it corrects for that and all these outliers by using a formula that takes into account how far each value is from the distribution mean. So if we were to go back to my spread here, right, 74, 75, 76, 79, 80, it would look at my mean, which is 79.5, and figure out how far each observation was from 79.5. So 74 would be 5.5, 75 would be 4.5, 76 would be 3.5, 79 would be 0.5, and it would add it all up, and then it would create a measure of dispersion inside that data set, and it would use every value. So standard deviation is a much better, okay, I missed, standard deviation is a much better, it's a much better measure of deviation than the range. So here we have the formula. You don't need to memorize the formula. You don't need to do calculations from the formula. I'm just putting the formula up there for your reference. Here, the standard deviation is the sigma, and it shows the formula for it, and it tells you everything that all the values inside there. So if you wanted to, you could actually figure out the standard deviation from the golf scores if you want to. You could put that in there. And what you would be doing is basically summing up those differences, squaring them, and that squaring makes it where you always have a positive number for dispersion. Standard deviation is never negative. You can't have negative dispersion. The least dispersion you can have is 0, and that's where there's no variance at all inside. So that square actually makes sure that that number is positive. Remember, see that denominator there where n minus 1, you would be 8 minus 1 because you have 8 values in there, and you get a measure of standard deviation from that. You're not required to do that in this class. I'm just letting you know what you could do. The square of the standard deviation is called the variance of the deviation. So if you square the standard deviation, you get the variance. In a normally distributed frequency distribution, you can see that 68% of observations lie within one standard deviation of the mean, 95% lie within two standard deviations, and 99.7% lie within three standard deviations of the mean in a normally distributed set of data. For instance, income is not normally distributed because it's got the long skew of the incomes of the rich people. But when for instance, IQ scores are normally distributed where the mean, median, and mode are all in the center of the distribution, and you have tails that go out like this. The standard deviation tells you where the dispersion is and how many people are how close to the mean. So the range, I already talked about the range, but just to let you know, the range is the difference between the highest and the lowest values in a distribution. The range in our previous example was 83 minus 74, which equals 9. The range is particularly sensitive to presence of outliers. For instance, if I were to shoot a very high golf score in one round, say a 92, didn't quite shoot 92 yesterday, but that's the example I used. I didn't quite get that high, but I got high. The highest value in the above distribution would be 92, and the other values remain the same. So the range would be 92 minus 74, which is 18. See how one value in that situation just doubles the range just like that. So that's the flaw in the range. It only takes into account two values in your distribution, and so it doesn't really work very well if there's any outliers. Standard deviation. The second measure of dispersion corrects for this by using a formula that takes into account how far each value is from the distribution mean. I already put that in the previous slide. I'm repeating myself on this slide. Sorry about that. But the square of the standard distribution is called the variance. That was there. And in a normally distributed frequency distribution, it is seen that 68% of the observations lie within one standard deviation, 95% within two standard deviations, 99.7% within three standard deviations. That will be more important when you take statistics, but it gives you a good idea what's going on now, because that is very useful with the t-score. So remember that with the t-score, we need to be in that 5% range where there's a less than 5% chance that this data is skews from the mean by chance. Well, the standard deviation helps us find that. Okay, thank you very much. That is the end of the video for Chapter 8. I hope this video helps you with your test. I think it will. And I hope that you have a great day. I want you to make sure to please contact me by email or phone, or we can Zoom if you like. Email is the easiest way to get in contact with me quickly. I usually answer those emails within 24 hours. And then if we need to arrange a longer conversation, we can do that. So please get in contact with me if you have any questions. And I think this video will help you with the test. So I wish you well on that. Thank you.